Hello. Today we're going to talk about osmoregulation, and the corresponding objective is describe how the kidneys create and use an osmotic gradient to regulate urine concentration and volume. So let's start with some examples that we're familiar with. If you are exercising and it's really hot outside, you're going to sweat a lot and you're going to feel dehydrated. Or if you're sitting on the porch and watching the people run around in the yard and you're drinking a bunch of tea or lemonade, you could get overhydrated. We've all had these experiences where we're either dehydrated or overhydrated, and yet we don't die. Like, it doesn't matter. Our body can dehydrate and overhydrate without any consequence. And the reason for that is because we have the kidneys. The kidneys are able to make subtle adjustments to maintain the appropriate concentration of our body fluids. If we didn't have the kidneys and then we overhydrated or dehydrated, it would be no good. So, reiterating what I just said, function of the kidneys is to make adjustments to maintain the correct concentration, which in our body is 300 milliosmoles. Quick review, what is osmolality? It's the solute concentration. Solute are like the ions that can dissolve in water, like sodium and chloride. So how much salt do we have in the water? 1 osmol is equivalent to 1 mole of a particle per kilogram water. And in the body, we have way smaller amounts, so we actually use milliosmoles. So 300 milliosmoles is what we want our osmolality to be in the body. So the kidneys keep the solute load of body fluids constant. We know that. We've established that already. So then the question is, how do they do that? By regulating urine concentration and volume. So the way the kidneys are able to keep our osmolality the same is by regulating urine concentration and volume. If we're dehydrated, the body will produce a small volume of concentrated urine. It's probably like a dark yellow. You notice that you don't pee very much. And when we're overhydrated, we have to pee a lot, and it could be almost clear. They do this by using a countercurrent mechanism. Countercurrent means that we have fluid going in opposite directions. So picture the nephron loop itself, like descending and ascending. That is one countercurrent. But then the nephron loop is also covered in blood vessels, and the fluid in the blood vessels is also countercurrent. So we have fluid flowing in opposite directions in two places. And as weird as that sounds, that's what allows the kidneys to regulate urine concentration and volume. So let's talk more about the types of countercurrent mechanisms. One is called a countercurrent multiplier, and this is the nephron loop. So the filtrate flows through the nephron loops, and remember how one side is permeable to water and one side is permeable to salt? So we're basically multiplying the power of the salt pumps, countercurrent multiplier. And then countercurrent exchanger is talking about the blood that's in the vessels that cover the nephron loop. The vessels that cover the nephron loop is called the vasa recta. Recta means straight, so basically like long blood cells or long blood vessels that are around them. And they're exchanging salt and water into the bloodstream. So picture this as reabsorption. When the nephron, something leaves the nephron, and then it's reabsorbed into the bloodstream so that it can be kept in the body. These two countercurrent mechanisms work together to produce a medullary osmotic gradient. So basically, the solute concentration in the medulla is different. It's not the 300 milliosmoles. And that concentration gradient is what allows the kidneys to be able to concentrate the urine. So, to say everything I just said all in one slide, the kidneys maintain constant osmolality of body fluids. How do they do this? by regulating urine concentration and volume. Remember, when we're dehydrated, it's a small volume of concentrated urine. When we're overhydrated, it's a large volume of dilute urine. How are they able to do that? By using countercurrent mechanisms to create a gradient, the medullary osmotic gradient. Okay, let's pause. Does that make any sense? Maybe go back and read about that if it doesn't, because the next thing we're going to look at is how they actually make the gradient. And this is some pretty cool stuff. So if you're ready, let's get into how we establish the gradient. So here's a picture of the gradient. We can see here's our nephron, and here is our glomerulus, PCT, nephron loop, DCT, and then collecting duct. This lighter color up here is the cortex, and then the part down here where the nephron loop starts is the medulla. And over here is our osmolality. So we can see the cortex is the same as our body at 300, but then we get a more and more concentrated gradient the deeper into the medulla we go. And this little nephron loop right here is called the countercurrent multiplier, and its job is to create that gradient. Let's take a look at how it's able to create the gradient. So, 3 reasons why it can create the gradient. Number 1 is we have the countercurrent flow, where the filtrate is flowing in opposite directions really close to each other. And then number 2 and 3 is the permeability of the epithelial cells in the nephron loop. The descending limb is permeable to water, so water can leave from here. But then the epithelial tissue actually changes, so this side is permeable to salts, or any solute really. So we can have sodium and chloride leaving here. So the descending limb is only permeable to water, that's number 2, and the ascending limb is only permeable to salt. Why does that matter? So if we look right here, when the filtrate is moving up the ascending limb, salt is pumped out. So we have active transport that's forcing salt to be able to leave the nephron and enter the space surrounding the nephron. The space around the nephron is called the interstitial fluid. Basically means like the space between things. So if salt is pumped out, there's going to be more salt out here. That's going to be an increased osmolality in the interstitial fluid. And now if you can imagine all of this salt that was just pumped out, that's going to cause water to leave the descending limb. Water follows stuff. Having a higher concentration of salt in the interstitial fluid is going to draw the water out. When water leaves the filtrate, now there's less water in here, that's going to increase the osmolality of the filtrate. And that's how we're getting really concentrated down here. And then, because we have an increased concentration of filtrate, that's why we pumped the salt out in the first place. So one more time from the top, the ascending limb pumps out salt. This increases the osmolality of the interstitial fluid. This increase in osmolality causes water to leave the descending limb. When water leaves the descending limb, it increases the osmolality of the filtrate. And that increased osmolality in the filtrate is why we had to pump salt out in the first place. This is a nice example of positive feedback. Sometimes it's hard to think of examples that males get to experience, and here's a good one to keep in mind. Now, why do we care about this? Here is kind of that same diagram, but we can actually see the gradient that it is creating. So originally the filtrate is isoosmotic to the blood, so it's at about 300, but then you can see as more and more and more water exit, we become more and more and more concentrated. And as it becomes more concentrated, that's why we pump the salt out. When we pump the salt out, the filtrate becomes less concentrated. And so the highest concentration is down here at the bottom of the loop. All right, so we have created a gradient. We've created a difference in concentration. Now we want to make sure that nothing happens to it. Like we went to all this effort to create the gradient, we need to be able to maintain it. that is where those blood vessels, the vasa recta, this is a simplified drawing of them, but if you can kind of imagine that they're covering both limbs of the nephron loop, they function as countercurrent exchangers. So they maintain the gradient by exchanging water and salt. Here's a diagram of that. So here we can see this is part of the vasa recta, and this could be near the descending nephron loop limb. Remember, the descending loop is the one that releases the water. So this part of the vasa recta is absorbing NaCl. And then down here, this is the part of the vasa recta that would be by the ascending loop that's permeable to salts. This is the part that's releasing the salt and taking in the water. So this basically, I'm going to read this. The countercurrent flow of fluid moves through two adjacent parallel sections of the vasa recta. So there we have the down and the up. And this exchange of sodium and water right there is what allows us to maintain the current. And then you might be wondering, like, this is all great, but why do we need a gradient? The reason we need a gradient is for the collecting ducts. So they are going to actually use the gradient to be able to adjust the osmolality of the urine. So we had to create this gradient in order for the collecting ducts to be able to dilute or concentrate urine. So established medullary osmotic gradient can now be used to form dilute or concentrated urine. Without the gradient, we would not be able to raise our urine concentration over 300 milliosmoles, and then we would not be able to conserve water. So basically, we would die without this gradient because we would pee out all of our water. Let's take a closer look at how. So this first situation is where you've been drinking a whole bunch of water, so you're overhydrated. If you drink a bunch of water, your fluid is going to have a decreased osmolality. You're more water, less concentration. When we have a lower osmolality, our body releases less ADH. ADH is the antidiuretic hormone that's able to put aquaporins in the collecting duct. But we're overhydrated, so we have decreased osmolality, so we don't release very much ADH. We don't have very many aquaporins. That means that most of the water is going to stay in this collecting duct, and then we're eventually going to pee it out. Let's contrast this with over here. We have a high concentration in our body fluids, which is the signal to release more ADH, and that adds more aquaporins to the collecting duct. Look at all these little blue arrows. Those can represent aquaporins. Because there's more aquaporins, there's lots of places for water to be able to leave the collecting duct, and then it's able to stay in the body, so we pee out a small volume of concentrated urine. Okay, I know that was a lot. Kind of mull it over, and then please reach out to me with your questions.